Hello everyone, I'm Taha from TU Berlin. Welcome to our talk Exploiting SNMP version 3 for router fingerprinting. This is a joint work with Oliver, Rob, and George. As networks become larger and more complex, it's important to monitor and manage them remotely. To address this need, the Simple Network Management Protocol, or SNMP for short, was first introduced in the 1980s and has since served as the de facto protocol for monitoring devices, diagnostic, and configuration management. SNMP has a long history of development that led to multiple revisions over the years. The first version suffered from poor security and performance. It relied on community string for authentication, which is simply a pre-shared plain text password with no support for any form of encryption. SNMP version 2 offered many improvements over the previous version, but it also increased the complexity of the protocol. Many different variants of this version were developed, with each having a different security model, but only a community-based version was widely adopted. Other variants were deemed obsolete due to their complexity and overhead. Ultimately, version 2 was not able to solve the security issues found in the first version. SNMP version 3 was standardized in 2002 and aims to address the security issues found in earlier versions by providing a means for secure authentication, encryption, and access control. Although SNMP version 3 should be popular by now, measurement studies up till now focused only on the community-based SNMP version 2. As you can see in this figure, the number of publicly accessible SNMP version 2 servers with the public community string has seen a steady decline since 2014. Currently, there are around 1.6 million IPv4 addresses that respond to SNMP version 2 requests. In this work, we will examine the adoption of SNMP version 3 and utilize our findings in solving some of the challenging internet measurement tasks. But first, let's take a look at the initial communication phase between two SNMP entities, a manager and an agent. SNMP version 3 replaces the community string authentication mechanism with a user-based security model. Due to the key localization employed by this version, the manager needs to know the engine ID of the agent in order to derive the appropriate key for authentication. Note that the engine ID is a persistent value that is used to identify the SNMP entity. We noticed that even if the manager sent unsolicited and unauthenticated requests, an agent will respond with its own engine ID as part of the synchronization process. Further, the agent will share some additional information, namely its engine time and engine boot values. Both of these values are used as part of the protection mechanism against replay attacks. The engine ID, engine boot, and engine time are all unique device identifiers. Furthermore, the engine ID can include some additional information, such as the MAC address of the device and the manufacturer private enterprise number. But what can we do with a simple discovery packet? We can use it to facilitate multiple internet measurement challenges, such as alias resolution, IPv4 and IPv6 dual stack detection, device vendor fingerprinting, and uptime analysis, all of which can be achieved with only a single packet per IP. Now let's see how we can use SNMP for alias and dual stack detection. Consider this router with three interfaces. We start by sending unsolicited packet to destination A. We note the response's three unique identifiers, the engine ID, engine boot, and engine time. After a short period of time, we send another unsolicited packet to destination B. If the returned unique identifiers matches the one we received from the first probe, then we can conclude that destination A and destination B are aliases. We can follow a similar approach to reach the same conclusion for destination C and destination M. To investigate the adoption of SNMP version 3, we use ZMAP to perform multiple IPv4 and IPv6 scanning campaigns. We used a single vantage point located in a well-connected data center in Germany. We target every routable IPv4 address and relied on the IPv6 hitless service for our IPv6 scan. We only sent a single unsolicited request per IP. We received more than 31 million responses for IPv4 and more than 180,000 responses for IPv6. But to ensure the accuracy of our alias resolution and fingerprinting results, we took a very conservative approach and applied the set of filters to the scanning results. For example, we remove responses where the engine time value is 0. Please refer to the paper for further detail regarding the filtering process. After the extensive filtering, we're left with 12.5 million responses for IPv4 and 140,000 for IPv6. Now let's take a look at some of our findings. Here we show the most popular vendors for all SNMP version 3 responsive devices. Overall, we were able to fingerprint and de-alias more than 4.6 million devices. One observation here is that the top 10 vendors cover more than 80% of the results. Next, we focused on the vendor popularity for SNMP version 3 routers. To identify a device as a router, we check if at least one of its IP addresses can be found in a publicly available traceroute dataset, such as Tribe Atlas and KBAS ITTK. Overall, we were able to identify more than 350,000 routers. We observed that only 4 vendors cover more than 95% of the routers running SNMP version 3. Next, we consider a case study of the largest 10 networks by the number of SNMP version 3 routers across multiple regions. In 6 out of the 10 networks, Cisco is the dominant vendor, while Huawei dominates in 2 European and 1 Asian networks. We also observed that most of these networks rely on a single vendor for the majority of their equipment. Finally, we use the engine time value to calculate the last reboot time of a router. Here we have a CDF for the time since the last reboot for all SNMP version 3 responsive routers. We can see that less than 25% of these routers had their last reboot more than a year before our scanning campaign. Further, around 70% of routers had at least one reboot since the beginning of this year. These results could indicate crashes, power outages, or potentially the last time a router has been updated. But why did we find a lot of IPs responding to unsolicited SNMP version 3 requests? To answer this question, we tested multiple router configurations in a lab environment. We found that by enabling the community-based SNMP version 2, a router will also respond to SNMP version 3 even without any explicit configuration. We suspect that this is not the intended behavior and reached out to major vendor for clarification. They confirmed that this is indeed not intended and informed us about the possible countermeasures. We plan on testing additional implementations for more routers vendor in the near future. To learn more about this work or request access to our most recent results, please visit SNMPv3.io. To summarize, we investigated the adoption of SNMP version 3. We found more than 31 million IPs responding to unsolicited and unauthenticated requests. We used our finding to detect IP aliases and dual-stack interfaces for more than 4.6 million devices. We used our fingerprinting results to gain some insight about router deployments and operation within more than 11,000 networks. Thank you for your attention, and we're happy to answer your questions.